Well, thank you, Dan. Thanks for putting this class up. And as I said, my name is Sumit Gupta, and I've been with Sun for more than 10 years. And most of the time, I've worked in storage-related technologies, and almost 75% of it worked on technologies which are related to fiber channel. When Dan asked me to put this class and thought about what should we talk about it, I thought it would be a good idea to go to start with fiber channel concepts, because that is the fiber channel initiator stack. So and fiber channel is a very big protocol, and it's not possible to actually cover everything in one class. So what I thought is that I'll probably go over a little bit of history of fiber channel and try to describe how we started from parallel SCSI and how we got here where we are today. And in that process, I'll try to explain some of the components and some of the basic elements which make up the entire transaction on the fiber channels, on the fiber channel track. And we were also hoping to do the analyzer today, but hopefully we'll do that tomorrow. So with that said, let's dive into it. So here is our agenda. We'll talk a little bit about parallel SCSI and how the FC evolution happened. And as a part of that evolution, how different topologies came into existence. And in the last, the topic which is most confusing for a lot of people is the different numbers. So there are worldwide names, port IDs, loop IDs, target IDs, LUN numbers, GUIDs. So I'll probably try to go through a description of what are the various numbers and what they actually mean. Okay, so almost 9 years ago, I was in a very similar situation, and I was trying to give a presentation on fiber channel. And whenever you give a presentation on fiber channel, the first slide is always parallel SCSI, because you try to tell what was wrong with parallel SCSI. And I was in a room full of people, and I put this slide on the projector, and I didn't realize that people in that room had spent most of their career working on parallel SCSI. So we actually spent 45 minutes on this slide, and it was a 1-hour presentation. So hopefully we don't do that today, because it's been 10 years and people know more about fiber channel now. So parallel SCSI was basically 5 megabyte per second. Initially it started with 8-bit wide bus, and then it evolved into something we called fast SCSI, which was 10 megabyte per second. And then there was also another version of fast SCSI called fast wide, which was 20 megabyte per second. It was 16-bit wide bus. And they eventually went to ultra SCSI, which became 40 megabyte per second. Of course, now you have ultra 320, which is much, much faster. But this is how the speeds were. And the biggest problem with parallel SCSI, and I used to do a lot of testing with parallel SCSI, is that you touch the cable, it moves a little bit, you start getting parity errors. And you can only have like a feet, 1 foot wide and 1 foot long cable, and you can only have like 12 devices. So there was a lot of connectivity issues with parallel SCSI. So you could only connect 16 devices, and the reality was if you connected 16 devices, nothing will work. You could never really go above 12 devices. There was a 32-bit version of it where you could connect, in theory, 32 devices, although I have never experienced that. The device addresses were fixed, so you had jumper on the device where you say this device is SCSI ID 7, this device is SCSI ID 6, and all the addressing has to be predetermined. And if 2 devices had the same address, you will start getting parity errors. Small cable length, and this was one of a very big problem. It's called large selection timeout. Is that the way system worked, that there is no way for the system to know how many devices are there. So what it will do is it will try to talk to every device to figure out how many devices are there. As a part of talking to every device, it does something called selection. And the only way for it to know that there is no device on the bus for this device number is to wait for a timeout. And selection timeout was 250 milliseconds. So if you had like couple of storage HBAs in a system, and you have a big SD.conf file, your system will take about 3 to 4 hours to boot, because what it's doing is it's actually trying to select all those devices which do not exist. So large selection timeout was a huge problem. In fact, we made a change in the device drivers to to shrink it from 250 millisecond to 1 millisecond, and that was a tunable. But of course, that only worked with a certain set of qualified devices. If you try to use it with non-qualified devices, that did not work. So this was a huge problem. And then somewhere around 1996, Sun was trying to bring up a system called Excalibur. It was codename Excalibur, and I think the official name is Sunblade 1000. So what we did was we actually took a fiber channel chip and put it on the motherboard of that system. And that's when things got really interesting, because now we were in serial mode all of a sudden from parallel, and we were in sort of uncharted water. So let's go into next slide. So initially, the fiber channel solution was called fiber channel private loop. And what it did was it basically took a bunch of devices, connected them sequentially one after the other, and that essentially gave a higher connectivity. As you can see, it gave 126 connectivity of 126 devices. The thing with fiber channel was that it is serial connectivity instead of parallel. So the SCSI bus is parallel, and the problem with parallel bus is that you are limited in speed, because you have skew between different lines, and you have noise and crosstalk between different lines, and that limits your speed. But when you go from parallel to serial, all of a sudden the speed goes from few megabytes or a couple of 100 megabytes to gigabytes. So the initial speed with fiber channel was 1 gigabyte. It has very high connectivity, 126 devices, both soft and hard addresses. So let's talk about that. A hard address is basically what you do with parallel SCSI. You have a jumper on the device. You set the device ID. You say, this device is SCSI ID 7. This device is SCSI ID 8. Soft address means we do not decide what is the address of the device. When the things are initializing, that's the time the device picks up an address. That's called a soft addresses. And I have a backup slide. It's called loop initialization process. Once I go through that, I will describe what is soft address. Along with the addresses, each device also had a unique identifier. It's kind of like your Ethernet card, right? Ethernet card has a MAC address and an IP address. So an IP address is, if it is a static IP address, you can think that as a hard address. If it is a DHCP IP address, you can think of it as a soft address. And the MAC address of the card is the unique worldwide name, so sort of relating it to networking side. So each device on fiber channel has a unique worldwide name. And that helped a lot, because now you can identify a device and say what went wrong with this unique worldwide name. Of course, when you go serial, the cable lengths all of a sudden are much longer because you don't have skew problem. So the cable lengths were 30 meters for the copper, and it goes to 10 kilometers for the optical cables. So full duplex is another advantage which fiber channel brought, because in parallel SCSI, the data bus was 8-bit wide, and you could only use it to transfer data either from the initiator to the target or from target to initiator, but not both at the same time. But with fiber channel, we were able to do full duplex. And I put in some terminology which is used very often with fiber channel. N port is basically node. A fiber channel node is called N port, and L port is loop. So when a node is operating in a point-to-point manner, means it's talking directly to the initiator, talking directly to the target, or a target talking directly to the initiator, it's called an N port. When you are in a loop topology, which means you have 126 or lesser devices connected in a loop, the port is called an L port. Sometimes the port has the ability to act as an N port and an L port at the same time. In that case, it's called an NL port. So okay, I probably should have put this slide before the other one, but so this slide describes the private loop solution. So you can see all the devices have a transmit and a receive, and the transmit is connected to the receive, and it forms a loop. So what happens is, if this device wants to talk to this device, it does something known as arbitration. So it will send a arbitrations to this device, it looks at the arbitration data set, and in that, it will see that this arbitration is not meant for me. So it will not act, it will act as a simple bypass and send the arbitration to the next device. This keeps on happening until it reaches the correct device address, which knows that the arbitration is for me. What this device does, it consumes the arbitration in the sense that it translates arbitration into idle, and the idle basically starts traveling back. So when that happens and this device gets back, it knows that the other device is now selected. So at this point, it's kind of a point-to-point topology. So all these devices in between are acting in a bypassed manner. They're not really participating in the activity, except that they are simply passing the frames from the receive to the transmit. So these two devices are connected point to point until they do a close. When they do a close, then everybody knows that, okay, the loop is available again, and somebody else can do arbitration and utilize the loop. So you can see that multiple devices are connected to each other, but still they can communicate to each other in a point-to-point manner. But there is a disadvantage of this topology is that you have to do an arbitration and you have to do a close for every transaction. When we go into switch, we'll see that the arbitration goes away and the selection goes away and close goes away. So with arbitration, the problem was that it took a lot of time, and if you really put 126 devices on a loop, then arbitration will take forever. Sometimes some devices will actually time out because they will think that the arbitration would never reach back. So the solution to solve that problem was to do something called segmented loop. Segmented loop basically said we took a device, a switch or a hub, and it provided like 4 ports, and each port will be its own individual private loop. Internally, all the ports will think that they are connected to each other and it's one big giant loop. But what the hub will do is it will look at the arbitration and it will find out, okay, this arbitration belongs to this port. So it will bypass all the ports. It will actually bypass a larger portion of the loop and go directly to the device for which the arbitration is meant for. So that was called segmented loop. Initial fiber channel switches actually implemented segmented loop as a part of the switch. It reduced the arbitration delay. It provided more fault tolerance because things were more fast now and there were less timeouts. Again, dual loop devices. So initial Seagate drives had the ability to participate in two private loops at the same time, and they did that because they wanted to provide multipathing. So if you had a segmented loop, you could actually make the two loops part of the two different segments, and as a result of which you provide better connectivity. And as I said, the initial switches actually had SL ports, which are segmented loop ports, as a part of the switch solution. So this is a diagram of a fiber channel switch. And as you can see, it actually, so this is the switch portion of it, and these are the individual devices. A N port can be an initiator or a target. So you can see that here the loop is gone. Everything is connected directly point to point. And what's happening here is that if this device wants to talk to this device, it simply sends a frame to the switch. The switch receives the frame and forwards it to this N port. So there is no arbitration, there is no open, there is no close. That's why it's a fiber channel fabric topology, or when a switch is involved, it's considered faster than when you do private loop. So this is a slide about fiber channel switch. As you can see, a switch does not involve any arbitration delay. Also with switch, the address space went from 8-bit to 24-bit. So in a private loop, the address space, the address which is used to talk to different devices was 8-bit wide. But with switch, it actually went to 24-bit. And what that gives is, it gives us ability to cascade different switches together. And each switch, so it's kind of like an IP address, where you can actually create small networks or subnets and talk and route frame from one subnet to other subnet. The connectivity also on a switch increased because the switches come, so there were smaller switches which were 8 port wide, and then there was called director class switches, which went to 64 ports. So a switch provided ability to connect 64 devices directly in a point-to-point manner. And of course, if you use segmented loop, you can actually connect more devices, because you can make one port a loop, and on that loop you can connect multiple devices. Fabric point-to-point, as we talked, there's no longer a loop, it's a point-to-point connection. Switch was again duplex, and cascading via inter-switch links. So basically ISLs, this is again the networking concepts. You can create different subnets and connect different switches together. When you connect two switches together with a link, the switches are smart enough to figure out that it's a connection to another switch and not a connection to a device. And those links, which are between two switches, are called ISLs. Switches also provided an interesting feature called zoning, where you could actually take one switch and divide it into multiple virtual switches. So initially, they were called hard zones and soft zones. What is a hard zone? A hard zone is basically a way where the switch virtually does not allow any traffic between two zones. So you could actually go to the switch management GUI and say, these 4 ports belong to hard zone A, and these 4 ports belong to hard zone B. And in that case, the switch physically inside somehow disjointed those two in such a way that there was no possibility of any traffic going from hard zone A to hard zone B. And the problem with that hard zoning was that when you actually did cascading, you had to cascade hard zones together. So if you had two switches with two hard zones, and you want to route traffic from hard zone A to hard zone B of the switch B, you have to connect those zones together. Let me actually draw it on over here. Now I hard zone this switch so that it is a hard zone A and hard zone B. And I again hard zone this switch that it is hard zone A and hard zone B. So what this means is that there is no possibility of any traffic from this port to go on this port. So virtually these are two separate switches at this point. But the disadvantage is that if I have an initiator here and I have a target here and I have a connection here, I will not be able to talk to this target, because hard zoning literally separates it out. And so in order for that to do that, I need to do another ISL here. So this is ISL, inter-switch link. So this sort of limits the flexibility point of view, right? This, now you're no longer that flexible because you have to literally connect all the hard zones together. The solution for hard zoning was, hard zoning related issues was to go to soft zoning. In soft zoning, every switch has an entity called the name server. So what the name server does is it actually, when you want to know what is connected to the switch, you actually go to the name server, which is a special address, FFFFC. You go to that address and you do something called name server queries. And name server queries basically give you information about what ports are connected, what are their worldwide names, what are their port addresses. So what soft zoning did was, we went to the name server and told name server that if an initiator from this port comes, do not tell it about a target on this port. So basically you say, this port, this port, this port, this port are connected are part of one zone. And then you tell, so basically there can be an access to many ports. It doesn't really matter at this point. So you can tell the name server which ports belong to a zone, and you don't really have to physically divide the switch. So what happens is, when an initiator goes to a name server and the initiator belongs to zone A, the name server will only tell it about devices of zone A. If the initiator belongs to zone B, the name server will only tell it about the devices which are in zone B. But the disadvantage is that if an initiator is not a good citizen and actually starts talking to the devices and it somehow knows about the devices which are not a part of zone A, it can actually send traffic to those devices. So if an initiator belongs to zone A, but it sends a IO to a zone B, that IO will succeed, because the switch is not physically divided. The division is really at the name server level, and the name server is saying these devices belong to a zone. So it's sort of a cooperative zoning and not really enforced zoning.
Would this be a good point to mention something about host-based zoning too? Or not?
Yeah, I mean, I think so. Although when we go to host-based zoning, people start looking into LUN level zoning instead of target port level.
For host-based